So this is usually one of the steps in which we solve a general optimization problem. But because we are not expected to have exact approximation using a second order Taylor series, this delta S may not lead us to exactly the optimum, right? It depends on exactly how smooth this objective function is. It also depends on how far you have to move to get to this optimal point. So this is just a single step, right, in our optimization. So this is like our delta S of 1. And then my S1 is going to be equal to S0 plus delta S1. All right, so that is going to give me hopefully a more optimal, though not the optimal parameter value, and allows me to perform my next step. What is my next step? My next step is to use a better Taylor series approximation, right? Starting at this S1, it is equal to JS1 plus the first order term at S1 times my new delta S. Here, my delta S is going to be redefined as S minus S1, right? Plus half of delta S transpose the Hessian at a different point, S1 times delta S. Now, optimization of this new approximation gives us delta S2, which is equal to, again, minus H, so H inverse times G, except for the H and G are updated. So now if I denote this as H0 and G0, which corresponds to the Hessian and gradient at S0, this is my H1 and G1. All right. So now this gives my S2. My S2 is going to be S1 plus delta S2, and etc., etc. So this is an iterative method. I'm going to be approaching a better and better solution to the optimization problem as I iterate. And if you pay attention to this and remember something we have discussed before when we are learning the ODE part of this class, you might find a similarity between this iterative procedure and the iterative procedure we used to solve a nonlinear equation when you use an implicit time-stepping method for ODEs. Actually, this is actually exactly the same method, because this method is called the Newton's iteration. Okay, and in previously, I think we called it the Newton-Raphson method. Right, so the Newton's iterations is applied both for solving nonlinear equations and for solving optimization problems, except for in optimization problem, if you apply the same procedure for solving the nonlinear equation, the nonlinear equation here is actually the equation that gives you the gradient of J with respect to S equal to 0. This is the nonlinear equation we are solving using the Newton's method here, right? And in Newton's method, we are constantly, in every iteration, we are evaluating the residual of this nonlinear equation. In this case, the residual is the gradient. In Newton's method, at every iteration, we are evaluating the derivative of the objective function, called Jacobian, right? The derivative of a vector-valued function with respect to its vector-valued arguments is called the Jacobian. And in the Jacobian of the gradient is the Hessian. So this is basically the same method we use to solve nonlinear equations. Now it's used for optimization. Now, in optimization, if you remember, the Newton's method for solving nonlinear equations has a big annoying feature, is that it converges really fast if your initial guess is very close to the actual solution. It's not as annoying when you are solving ODEs, because you know that if you're choosing a small enough time step, my last time step solution is pretty close to the next time step solution. So I actually have a solution that I know is going to be pretty close. In optimization, though, we don't have that luxury, right? So in optimization, we usually need a little bit more safeguarding when we are applying the Newton's method. So we are going to discuss a little bit about the most common way to safeguard a Newton's iteration to prevent it from diverging.